There are n employees, numbered 0 through n-1. Each names exactly one favorite coworker, not themselves. They sit at a round table and will show up only if that favorite person is in the adjacent seat. Example 1, favorite is 2, 2, 1, 2. Employees 0 and 3 want to sit beside 2, 1 and 2 want each other. We can invite employees 0, 1, and 2 around the table so every attendee sits next to their favorite. Employee 3 cannot join without breaking someone else's adjacency. The answer is 3. Example 2, favorite is 3, 0, 1, 4, 1. Employees 0, 1, 3, and 4 form a 4-person cycle. Employee 2 feeds into that cycle but cannot be seated without breaking adjacency. The answer is 4. Imagine you are planning seating arrangements for a massive dinner. Every single guest has exactly one favorite person they demand to sit next to. If you follow these arrows from guest to guest, a fascinating shape emerges. Because everyone must point to someone, you will always end up walking in circles. This graph structure naturally forms closed cycles with long tails of people leading into them. There are two completely different ways to seat these guests. The first scenario is a large cycle, a ring of 3 or more people. If 4 people form a perfect mutual loop, they take up the whole table. Sadly, anyone standing in the tail leading into this circle is completely locked out. You cannot invite them without breaking the circle's internal harmony. For large cycles, the maximum table size is simply the size of the cycle itself. But what if 2 people point directly at each other? This is a mutual pair, a cycle of size 2. This is where the magic happens. Because they only care about looking at each other, the outer arms of their seating arrangements are completely free. They do not care who sits on their other side. Because a mutual pair leaves their outer sides open, we can invite the single longest chain of people pointing to 1, and the single longest chain pointing to 2. They line up behind them in 2 long rows, 1 chain behind each member of the pair. Suddenly, a tiny pair of 2 can grow into a massive banquet table of 7 or 8 people. Here is our final engineering choice. Large cycles cannot be combined, you must pick the single brightest, biggest one available. But mutual pairs are incredibly cooperative. You can line up as many mutual pairs and their tail chains as you want around one giant perimeter. To find the ultimate answer, we calculate the biggest isolated loop, calculate the sum total of all mutual pair chains combined, and see which strategy yields the biggest guest list. To solve this in code, our first mission is to separate the tails from the loops. We use Kahn's algorithm for a topological sort. We count how many arrows point to each person, their in degree. Anyone with 0 votes is a dead-end tail. We drop them into a queue and process them. As we remove them from the graph, we chip away at the chains, peeling back the layers until the tail chains vanish, leaving behind nothing but the pure, naked cycles. While we are trimming those tails, we do not just throw them away, we measure them. We maintain a dynamic programming array to track the longest path leading into any person. Every time we pop a guest from our queue, we pass their chain length forward to their favorite person, incrementing it by 1. By the time the chain hits the cycle, the entry point of that cycle safely stores the exact length of the longest line trailing behind them. Finally, with the tails cleared and measured, we walk the remaining loops using a simple traversal. If we find a large cycle of size 3 or more, we count its length and track the single reigning champion. But if we find a mutual pair, we stop walking. We instantly pull their pre-calculated tail chain measurements, add them together, and dump that entire configuration into a collective pool. At the very end, we pit the single largest loop against the sum of all cooperative couples, and the maximum value wins. We solve step by step on favorite 2, 2, 1, 2. The same data as a directed graph, each employee points to their favorite neighbor. Phase 1 is Kahn's algorithm. Build the in-degree array, same as always. Enqueue every node with indegree 0. That is the con BFS frontier. While peeling, track max chain length, initialized to 1. Con dequeue, pop employee 0, remove that tail from the graph. Relax along the outgoing edge, pass chain length +1 to employee 2. Dequeue employee 3, another indegree 0 tail. Relax indegree on targets. Only the cyclic core 1 and 2 remains. Con peel finished. Tails are gone, only cycles remain. Now scan every employee index. Use a visited array so we never walk twice. Employee 0 was already peeled as a tail. Mark visited at index 0 and skip. Employee 3 was also a tail. Mark visited at index 3 and skip. Employee 1 is unvisited. Walk the cycle. Step 1, follow the arrow to employee 2. Step 2, follow the arrow back to employee 1. The cycle length is 2. Record that in max large cycle. The best cycle size so far is 2. Employee 2 is already on this cycle. For a mutual pair we stop walking and read cached chain lengths from max chain length. Index 1 has chain length 1, index 2 has length 2. 1 plus 2 is 3. Compare max large cycle against the pair pool. The answer is 3. Time is O of n, where n is the number of employees. Con peel touches each node once, and the cycle walk visits each index at most once. Space is O of n for indegree, chain lengths, visited flags, and the queue. 1 routine, indegrees, con peel, then cycles. N is the number of employees. Clear every indegree slot. For each employee index I. Read who I favorites. Bump indegree on that favorite person. Every max chain length starts at 1. Start with an empty queue. Scan for indegree 0 tails. Enqueue each tail index. Con peel while the queue is not empty. Pop cur from the queue front. Neighbor is favorite array at cur. Relax chain length into the neighbor. Drop indegree on the neighbor by 1. If neighbor is now a tail, enqueue it. Same function, second half, scan leftover cycles. Reset visited flags. Best large cycle size starts at 0. Mutual pair pool starts at 0. Try every index I. Only node still on a cycle, indegree positive and unvisited. Fresh list for this cycle. Start walking from I. Walk until cur was already visited. Mark cur visited. Append cur to cycle nodes. Step along favorite array. Cycle size is simply the list length. Mutual pair when the cycle has exactly 2 nodes. First person in the pair. Second person in the pair. Add both cached chain lengths. Accumulate into sum of mutual pairs. Otherwise it is a large cycle. Keep the best cycle size in max large cycle. Return the larger of the 2 champions.